Hello and welcome back. So it's time now to start learning how to solve equations that involve logarithms and exponentials. And it turns out that to solve those kinds of equations, we actually use logarithms and exponentials to help us do that. And so one of the properties that we need to be aware of when it comes to logarithms is that logarithmic functions are what we call one-to-one functions, and actually so are exponential functions. But for now, let me focus on the logarithmic function. So here's a graph, of your typical logarithmic function. And what we see here, when we say one-to-one, what we mean by that is that if I choose any x value, okay, on the x-axis, let me get my right color here, okay, whenever I choose an x value, let's say x sub o here, well, there is only one possible y value, or one possible functional value. And so here, the function f, f of x sub o, where x sub o is actually some value that we're plugging into the function, this is some real value. It's like some y value, and there's no other value that it can be. And that's what we call one-to-one. It means that whenever we plug in some x value into our function, there's only one possible y value. Now that's not, not most functions are not one-to-one. So for example, if we just take a look at the exponential, or the quadratic function, just the simple function f of x is equal to x squared. Here's a parabola. And what we see is that, you could have, some value here, a, right? And it gives me some function value or some y value right here. But we see that over here on this side, okay, there's another value of a that's not the same as this value of a that would also give me that same value. And so what happens then is if I were to write something like, f of, I don't know, let's say a divided by 2 into my function here. All right, and then I said, okay, and that is equal to f of, let's see, let's see, a minus 8, let's say, okay? Well, now it could very well be true, that these two values of the function could be equal to each other. So for example, if we were to let a be equal to 4, okay, well, 4 divided by 2 would be 2, and then plugging it into our function, 2 squared would give me a 4. Here, if I were to let a again, I can let a actually be 4 again, and then 4 minus 8 would be negative 4. I'm sorry, I guess I meant to say negative 6. So 4 minus 6 would give me a negative 2, and negative 2 squared would in fact be 4 again. And so these values could be the same, and even for values of a that were the same. But what would not be true is it would not be true that if you took away the function, that a divided by 2 is equal to a minus 8. Okay, because these values here, because of this property, I can plug in different values, okay, and get the same y value. It would not follow that these guys had to be equal. Just because the function was equal when I plugged in two different expressions doesn't mean that the expressions are equal. In fact, here we said a would be 2. Here we let, we said a was 4 and a was 4 here, but here, this expression, 4 divided by 2, is actually 2, and this expression, 4 minus 6, is actually equal to negative 2. So these guys are not the same. All right. On the other hand, though, with one-to-one functions and with logarithmic functions in particular, we can say that if I have, for example, the log base b of let's say something like how about a minus 2, so a minus 2, and we say that that is equal to the log base b of, let's say, a divided by 8. Well, if these functions are equal to each other, since there's only one value, since any value I plug in for the function can only give me one functional value, then when the functions are equal to each other, for two different expressions that I plug in, the only way that can happen is if the expressions themselves are equal to each other. So with logarithmic functions, I could now say that a minus 2 has to be equal to a divided by 8. And so that is a special property of logarithmic functions, and it arises from the fact that they are one-to-one functions. And that is something that's pretty powerful because this allows me to solve all sorts of equations that would involve logarithms and also exponential functions. And so let me give you some examples. In fact, if we did, if I actually put in a number here, let's say for my base, I just let this be something like 7, right? Okay, well then this means that since they have the same base, that I can write that a minus 2 has to be equal to a divided by 8. And I can multiply both sides by 8. This would give me 8a minus 16 is equal to a. Adding the 16 to this side, subtracting the a on this side, I would get 7a is equal to positive 16, and dividing, I would get a is equal to 16 over 7. And I can find that because I know these expressions have to be equal in order that the functions are equal with each other. Okay, so let's do another example. Okay, so let me come down here, give myself some room. Okay, let's see. Let's go with a different color. So how about we do this example? So let's do log base 16 of x plus log base 16 of 10x plus 3. Well, let's say that is equal to 1/2. Okay. Well, so here, the first thing that we see is that we can use our properties of logs. These guys are added together. We can use the sum to product, property of logarithms, and we can make this one logarithm where these guys are multiplied together. So I can write this equation as log base 16 of x times 10x plus 3. And we can say that's equal to 1/2. Well, the very property of logs say, well, this is saying, 16 to what power gives me this, and we're saying it's equal to 1/2. So what that means is that 16 to the power of 1/2 has to be equal to this guy right here, right? It has to be equal to x times 10x plus 3. And so now I can solve for x, and 16 to the power of 1/2 is the square root of 16, which is just 4. So 4 is equal to x times 10x plus 3. Okay, and so now if I distribute the x, I would get 4 is equal to 10x squared plus a 3x. And if I bring the 4 to this side, okay, what that's going to give me then is I've got 10x squared plus 3x minus a 4 would be equal to 0. Okay, and so now I can use the properties of, quadratic functions equal to 0. And let's see here. Can I factor this? If I just say what would give me a 3 in the middle. Here, if I say, 10 is what, 5 times 2. Let's try what? I guess maybe, well, let's see. No, let's try 4 times 1. Because let's see, if I say 5 times 1, yeah, that would be 5, and 2 times 4 would be 8. And so 8, if I can say 8 minus 5, I would get a positive 3. So yeah, so what I'll do is I will write this now as, let's see, it'd be 5x and 2x, right? And so here I've got a negative, so I'm going to let the, let's see, I'm going to let the 4 be positive and the 1 be negative, right? And so let's see, that's going to give me, yeah, so 5, and then I want 5 times 1, right? So I'll say minus 1, I think, and then plus 4, right, is equal to 0. So 5x times 2x gives me 10x squared, and 5x times a negative 1 would be negative 5x, and then we have an 8x that gives me my 3x, and then 4 times negative 1 is negative 4. And so here we see, okay, so my answers are, it would be x is equal to negative 4/5, and x is equal to positive 1/2. Now here's what you have to be careful with here. Even though logarithms are one-to-one functions, whenever we use this property that we used up here that we learned earlier, the sum to product property of logarithms, and we bring them together, we often do create an extraneous root, okay, a root that would not normally exist. And that's what we've done here, because -4/5, what you have to recognize is that in the original equation, I can't have a negative number for my x, right? For logarithms, that would be outside their domain. Just having log base 16 of x to say that it was -4/5, that would be outside of its domain. Here, if you plug in -4/5, you'll see -4/5 times 10 would give me, it'd be the 5 would go into the 10 two times, and 2 times the -4 would be a -8, right? Plus 3 would give me a -5, and then -4/5 times -5 would give me a positive 4, and that works, right? I think it works. Does that work? Yeah, because if I have 16, what do I have to raise 16 to get 4? And the answer would be 1/2. Yes. So, but here it wouldn't work in the original one. So we create an extraneous root there. So you have to recognize, and you have to be careful, just like in earlier equations that we learned, that this is actually an extraneous root. The only one that actually counts would be this one, because it's the one that you could plug into the original expression or the original equation and get an answer that makes sense. Okay, so I'm going to stop there, and in the next video we'll do a few more examples of solving equations involving logarithms and then also involving exponentials. Okay, I'll see you then.